When everybody looks one way, try to look the other way. When everybody's obsessed with macro, try to look at the little things, the ideas, the innovations, the creativity. And when everybody's obsessed with creativity, then maybe that's when you should be looking at macro. It's not a wisdom or anything like that, certainly not advice to your own work. But the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. And I think we're right now in a situation where we have a massive drawdown. Orange Capital Partners is down 27.4% for the year, which is in line sort of with almost anything that matters in the market, tech stocks, NASDAQ, all that stuff. But it's still, of course, unacceptable. Nevertheless, what are we doing? We're doing two things. We're focusing on surviving, which means we have to make sure our leverage, our cash, our cost structure within the fund, our cost structure at home, all these things can support further drawdowns, since we just don't know what's going to happen with the macro and the market. We're also not spending too much time with the macro and the market, not because it's not important, but because we just don't think we have a lot of things to say there. What we're doing though, and this is the purpose of this episode, is we're focusing on technologies, innovations, ideas, academic advancements in two particular areas. One is computer design, computer architecture, and the other is quantum machine learning. Actually, those two things are highly correlated, and we're going to explain why. The purpose of this particular episode is to give people a sense for what we're working on right now. And as we said many times, your daily agenda, what you're doing today, is going to determine who you're going to be tomorrow. This is Not Even Wrong podcast. It's May 1st, 2022. This is Crimtelco. It's a Sunday. There's no update. For the year, we're down 27.4%. The market is down 13.7%. We're underperforming by 13.7%. Your daily agenda determines who you're going to be tomorrow. So what are we doing today? We're doing two things about what's happening right now in the world of computation. One is we're doing the course with Onur Mutlu about computer architecture, which is a course. It's about a year old, so it was published last year. So it's pretty up to date, of course. But anyway, that's one thing we're doing. And the other thing we're doing is we're looking at quantum machine learning. And this episode is going to be dedicated to quantum machine learning. The Onur Mutlu course we already had an episode. We're going to continue with the episodes. As I said, I'm not sure how I'm going to structure both of these subjects. So the computer design, computer architecture lectures, and the quantum machine learning lectures. Maybe I'm going to do it sort of Brett Hall style, just go lecture by lecture, chapter by chapter, or maybe I'll just summarize a couple of ideas. So I'll see how it goes. But this particular episode is dedicated to quantum machine learning. What is quantum machine learning? It's using the power of quantum computers to accelerate or enable certain problems in machine learning that classical computers either cannot do as well or cannot do at all. Where do we stand right now? The reason we're interested in this is for two reasons. One is it's actually complementary with what's happening in computer architecture. Onur Mutlu says it several times in his introductory lecture. The future of computer architecture is going to be focused on memory, energy efficiency, and of course, by maintaining cost and performance. So memory is directly related to quantum machine learning. One of the big advantages of quantum computers or quantum mechanics is that there is a theoretical possibility using quantum mechanics to incredibly accelerate memory, in a sense that you can store enormous amounts of data potentially just with one photon. So you can save space and energy and store many orders of magnitude more data in the same space and energy than you can with classical memory. So this is one of the big ideas. I am not an engineer or technical, so these lectures are not technical, of course, but nevertheless, we're doing a course now at Toronto University is offering an EDX course, so we're doing that course. And we've also listened to a lecture of Seth Lloyd. He gave a lecture in Japan about this. And this particular episode now is summarizing Seth Lloyd's lecture. This is the fundamental idea of quantum machine learning. So what's happening here? What machine learning is probably going to be able to do in the near future with quantum computers is to do BLAST, which is basic linear algebra subroutines. So things like principal component analysis, least square measurements, eigenvector and eigenvalue measurements, those sort of things, solving linear equations. So things that we're all familiar with MATLAB. People who've done Andrew Ng's course back then when I did it in 2012 was on MATLAB. Today it's, I'm sure, on Python. But all these linear algebra problems can be accelerated with quantum computers. And I want to focus, like Seth Lloyd did in this lecture, I want to focus on principal component analysis. So what's happening here is, in a nutshell, is the following. So what is machine learning? Machine learning is you want computers to do things without explicitly programming them to do them. So you want them to read data and to then learn something from the data, and then when new data comes, you want those computers to react in a certain way or do something that is driven by the data. So this is in line with Software 2.0, Andrej Karpathy's ideas. This is in line with what pretty much anybody's doing with machine learning. So Google learns from people doing searches, and then when a new search comes in, which is a new data point, Google uses some sort of algorithm to determine what to offer the person in terms of result. Andrej Karpathy and Tesla are using data which is basically camera data to drive a car. People in the robotic space use, again, visual data to make robots move, and so on and so forth. So if we now dare to be a little bit more technical, let's focus on principal component analysis. What is principal component analysis? You have let's say, a massive matrix of data, and you want to find out the principal components of that data. So you want to summarize the whole matrix. Let's say there's 1 trillion data points in a matrix, and you can find the principal components or the vectors that determine that particular data set. Or if, in other words, you reduce the data set to the principal components, so the vectors that are enough to reconstruct the same data set if you got new piece of data. So for example, if you see a curve in the road, you can then reduce that pixel set or that data set which determines the road. You can reduce that to whatever its principal components are, and then when a new data set comes in, so let's say the same, let's say you see a road, you can then transfer that, use that principal component, match it. You say, okay, this is a road because I stored what a road represents in terms of principal components, and then match it against what you see, and then hence decide, okay, I have to turn left. So in linear algebra terms, it means that you receive data, the data gets read, reduced to its principal components, matched with what is in the database, which matches this principal components that determine a road. You determine it's a road, and then from there you infer that you have to make a turn. One of the algorithms that allows you to do this. I'm trying to be very high level here for people who are not familiar with linear algebra. So think about it like you have a lot of data that represent a curve, and you want to reduce that curve to its principal component. So things that you can't omit. There's a lot of things you can omit. You can omit probably, the pavement. I mean, they're all the same pixels, but you can't omit where the curve starts hitting, where the pavement starts curving, and where on the left side is sand and on the right side is pavement. So those are the kinds of things that you can't omit. And this is there's other ways to do this. Of course, there's also the neural networks, and there's support vector machines and things like that. These are all algorithms that do different things, but in a nutshell do the same thing, which is, again, try to classify what they see, and then try to take new information, use the classification memory that they have to find out what they see, and then act accordingly. So this is one thing, according to Seth Lloyd, that can be accelerated with quantum computers. Now, why can that be done? Now, this is, of course, where I'm trying to educate myself a little bit more, so I can't give full answers to that question right now. All I can do is say it can be accelerated with quantum computers. And I think the intuition is that a quantum computer can use quantum states of photons, for example, or atoms, or whatever the substrate is. It doesn't actually matter. But let's just say that you can have some sort of physical material which can be kept in a quantum state. And because it can be kept in a quantum state, you can represent a data set with a lot less things. Let's say you can represent a data set with 1 photon, for example. And because that 1 photon according to the Schrödinger equation, has a big, Hilbert space set of possible vector. It can represent a Hilbert space, very high dimensional vector space. You can represent lots of data. Now, of course, there's a problem in quantum computing that you learn probably in Quantum Computing 101. And that is that you can't actually read data or copy data in quantum computing. So what is the point of representing data? Let's say you have the data set of a curve, which can be stored in one photon and then read and acted accordingly. What is the purpose of that if you can't actually read the information according to quantum computing theorems? Here's where the parallelism of quantum computing. You read data through a camera classically. You then perform a quantum computation on that data to get the principal components in one shot. You store it in quantum random access memory, one shot. You then use that data, which is stored, let's say the principal components, and operate on new data in one shot. Somehow you have to transfer the classical into quantum or the quantum into classical, but that let's not get too technical. The point here is that you have this multi-dimensional vector represented in the quantum state of a photon, and with that you can do one-shot calculations using just even classical methods right now. In the future, I can envision also quantum computation, things like entanglement can be used, interference, and all these things. I need to do more reading on the course itself, but the point here is that you have two massive accelerations here. One is the storage through quantum random access memory, and the other is the actual computation itself, which can be done in massive parallelism, because again, you can use the multidimensional vector, the Hilbert space representation within the photon of all the data that is necessary for that particular, let's say, pixel to be acted upon. And then you can act upon the new set of data without actually reading the stored data in the quantum random access memory. That's the way I understand it. That's, I think, what Seth Lloyd is trying to say in his lecture when he talks about that he was trying to sell this particular item to Google and things like that. Anyway, I don't want to go into too much detail here. The point, again, I will hopefully be able to get more meat around the bone, but the point of this particular episode is, again, to give people a sense for what we're doing right now. The reason we're doing this is because we believe that what we're doing today is going to determine who we are tomorrow. And how are we actually implementing this into our portfolio? Well, are we investing in quantum machine learning? Of course, we're not investing because we can't. We don't even know where to start if we want to do that. But what we can do is educate ourselves, have a good understanding of where computation is going, and then monitor our portfolio companies, and then hopefully either entice them to start implementing those ideas, or at least if they don't do that, we can then find other ideas where these ideas can be implemented. Just to give a bit of more meat around the bone here also, when we looked at machine learning in 2012, that's I think when I did the Andrew Ng course, and we just did the whole linear algebra there, we did the course and all that, and then we came across NVIDIA and we realized, well, there's a huge synergy here between what NVIDIA is doing with graphics and what the machine learning workloads of the near future will be. And actually we were right about that. Even though we didn't make too much money with NVIDIA, we made a lot of money with Tesla, and partly because when Tesla started using machine learning for computer vision, and they said, that's enough, we can do it with machine learning and computer vision, we had a lot of confidence that that's going to work. Now, we don't know the actual engineering details, and a lot of course, the hair is always in the detail, but we knew that the concept is right, and that gives you a lot of confidence as a hedge fund manager to concentrate your capital when you have an understanding of the underlying technology, and when you understand the thinking of people like Elon Musk when they deploy technology, like he did when he decided to go full on computer vision, when he hired Andrei Karpathy and he got rid of NVIDIA, which was a good solution. NVIDIA was a good solution, but it's a general purpose solution which wasn't good enough for Tesla. The future is solved for exactly that problem, because quantum access random memory actually is, quantum random access memory is going to solve for memory in terms of enabling the read and operation on orders of magnitude more data with orders of magnitude less space and energy. This is part of the application. It's almost a side project right now, because most people are obsessed with things like increase the speed of reading the data. But you know, if you listen to Onur Mutlu, the speed is one of the problems, but it's the back and forth. It's the problem that you constantly have to fetch data back and forth, which is the biggest bottleneck, which is killing a lot of energy, and it is very costly. So if you can find a way to, in one shot, get all the memory that you need and act upon new data without going back and forth. And this is one of Onur Mutlu's biggest problems, the back and forth. How do you solve that? Quantum random access memory does that. So, for example, the big application where we see, and this is hopefully the road that we will see Tesla will go in the next 2 to 3 years, is to use quantum machine learning to start developing animation. And with that animation, what we mean is you animate the real world using machine learning, so you don't hard code it in a lot of like video games, but you use, let's say you take a picture of a road in Alaska, or you drive down the road in Alaska, and you use that to train either through supervised or even unsupervised learning, use quantum machine learning to then train a model and create billions of versions of that road in Alaska, the city of Naples, San Francisco, the roads in Switzerland, all that, basically the whole world. And then the car can, through self-supervised reinforcement learning, learn how to drive. This, in our view, is going to be the future of full self-driving, where we're going to see, again, massive orders of magnitude better performances in terms of driving, in terms of using less energy, and all of these things will then combine, hopefully fall into place, and we will see the application of full self-driving finally realized. Hopefully Tesla will jump on that bandwagon. It doesn't look like that right now. Musk doesn't talk about quantum machine learning. I think we're a bit early on this one. It is just sort of trickling out of academia into the more popular science world. Let's say Quantum Magazine has just written about it. I mean, Seth Lloyd gave this lecture years ago, maybe 2 or 3 years ago in Japan. But it just takes years for academics to grasp a concept, and then for the concept to spill over into the venture capital community or the corporate community. We believe we're just right now at the cusp of such a technological development. The purpose of Orange Capital Partners is to generate wealth by investing in fundamentally new concepts and engineering practices, and this is exactly what we are talking about here. This is a fundamentally new concept and engineering practice with large impact, and we're looking at it right now. Hopefully our portfolio will be driven by this particular vector in the near future. So to summarize, quantum machine learning is at the cusp of being realized. It's solving for BLAST, which is basic linear algebra subroutines, which are major subroutines used in current machine learning workloads. So if we combine those two vectors, we see that there's a very high chance in the next 2 to 3 years, we have orders of magnitude faster data analysis tools, also less energy usage for this much faster data analysis. We have solutions such as potentially better animation to do self-supervised learning for self-driving cars. So we hope that in the next 2 to 3 years, we will see this application, in particular in full self-driving and in the genomic space. Thank you.